All right, welcome back to the infrared spectroscopy part 3. So before we start our lesson today, I want to say the IR is useful for simple checking of functional group, and for more details on the organic portion of the molecule, you need help of the NMR or other instrumentation. And in order to use IR, first you have to analyze the functional group during the changes that you are observing or the structure you are looking at. And you check the polarity and types of bond and their atomic numbers and so on. Those are changing the signals on the x-axis and y-axis and their shape. And also then once you match them, you can connect with the typical features of the functional group, including wave numbers and intensity and the shapes. Then today we'll be focusing on, while we are practicing with the typical ones, I'm going to mention about the variations. Depends on the neighbors, such as, presence of a double bond, or presence of the electronegative functional group, or some other things, including size of the rings and etc. Briefly, even for a functional group like CH2 NH2, some stretching vibrations, in particular asymmetric vibration and symmetric vibration. Though they are referring to the same functional group, stretching vibration, they have different frequencies, and they will also have a different intensity due to the different amount of the dipole moment you are causing by the vibration. So the IR is not checking functional group, and also IR is not checking vibration. IR is active, detecting only the type of vibration that generates changes in the polarity and dipole moment. In addition, generally speaking, bending vibration gets the smaller number due to the smaller force constant, since it's not changing bond distance. And the stretchings are normally getting higher number of the frequency. And then among stretching, asymmetric usually has greater number than the symmetric. Then the single bond with the hydrogens with the other atom, and triple bond, double bond, single bond. Nonpolar bonds, weaker absorption, and then more polar one, stronger, and the extremely polar functional group gives very strong signals. And then OHs and NHs, due to the potential hydrogen bond, rather broad, and the two peaks for the NH, stretching and symmetric and asymmetric stretchings, and NH only one stretching, OH, and then carboxylic OH, free OH, sp3ch, sp2ch, sp3ch below 3000, and the sp3ch normally is coming in a bunch, so it normally is tall. And then aldehyde signals at 28 something to 2700 something. Then the aldehyde, the triple bond of carbons and the triple bond of nitrogens, I hope you remember. And then the carbonyl comes around 1700 plus minus some, and then carbon-carbon double bond, couple or multiple, and the intensity varies, depends on the attachment on it. And then you have a bending vibration come in. It's covering up most of the weak signals of stretchings, but you can see the polar bonds like a CO or CCl, CBr, or some other some other benzene ring isomers. All right, so let's look at this spectrum of a compound. What do you find? And first, you see this big bunch of the signals, and you notice 3000 right here. If you draw a line, all these signals are below 3000, but very close. So this box here, between 3000 and 2000, was a box for number 1, sp carbon-carbon triple bond or carbon-nitrogen triple bond. But you know that is coming around 22. So it's here and nothing present. And this is very close to the 3000, meaning this is a CH of sp3. And there are many of them, and it's very intense, meaning you have a lot of CHs there, and the very different modes giving different CH, sp3 carbon H bond. There could be CH3 and CH2 and CHs, but also CH3 can have a various number of stretchings. And you notice that there are some bending vibrations, and there could be also carbon-carbon bond, but there's no way we can figure that out. But I believe these are the bending vibrations. So that's the only thing we see. And in fact, this is the IR spectrum of 12 carbon compound, alkane. So it's a dodecane. Okay, so here you have another spectrum. What do you see? I wouldn't give any consideration for these small peaks yet, especially the peaks under 1450, this region with the small intensities. I'm not gonna try to assign unless I have some sort of quantum mechanical reference about the symmetry of vibration modes. Okay, so again, I'm gonna pay attention to this big signal starting from the left side, and this is normally, because it's close to 3000, is the CH, and carefully you read the number 3000 here. You go up and you see this a little spike on the shoulder of this big signal is above 3000. And then these are below 3000, and there are a couple other smaller signals. I think this can be very important practice for you, the practical knowledge. Yeah, this is greater than 3000, so you suspect, as we did before, this to be either hydrogens on sp2 carbon or sp carbon. Then we said that we need to check whether we have double bond carbon or triple bonded carbon. For triple bonded alkyne carbon, we are looking at this region 22 here, around here, and you don't see any. And you might say this could be, and honestly it could be, if you have a triple bond that's the middle of the chain, symmetrical. I said it can be very weak. This is extremely weak. So I'm not gonna say this is yet. And also the number is not quite 22. But sometimes we'll have to come back to this and say this could be. Depends on situation. But for now, we have to assign the more trustable signals and do the structural elucidation first, then see how it works out. Okay, that's the practical learning you need to get. So ignoring this for now, I don't have triple bond, but double bond comes around, I said 1600 to 1400 something. So in this region, I see at least one and maybe two rather strong-ish peaks. And 1450, that's where the bending vibration starts. So maybe this and this and this, they could be from bending vibration, but still you have this intense one, so you cannot ignore this, and that's a trustable signal to be double bond. And combining the fact that you have this signal over 3000 correspond to sp2 carbon holding hydrogen, that's stretching vibration, and you have a double bond carbon signal, you can assume that you have actually alkene with a hydrogen on it, and you have a lot of sp3 carbon hydrogen signals here going on. So pretty much we can say we have alkene. But how about this one? And this is one of the I think most significant like impurity peak or some side peaks, because it's at around 27, you know, 27 something. It's the CH of the aldehyde, and then 28 is buried under here, so you don't see it. So normally when you get this, you have to suspect the presence of aldehyde. Then I mentioned that in order to have aldehyde CH, you also have to have a CO double bond. And where? Double bond region. And the CO double bond is 1700 plus minus something. You come here, 1700 is quite empty. CO double bond cannot be this weak. CO double bond is polar, so the absorbance will be normally tall, like this. So we don't have carbonyl group, so this cannot be aldehyde. So we ignore the possibility of aldehyde. So we conclude this to be alkene. And for the intermediate student, not a beginner one, I can tell you that the intensity of this double bond is very unusual. This can be told because, like I said, you know, earlier, if you think of the symmetric curve, you can imagine the curve can give you the intensity up to here. So the actual intensity for the CH may not be as tall as like from here 0 to the all the way here, almost like 85 or something percent. It maybe is only like 10% or a little more. So that's okay. But this is quite fat for the double bond and carbon-carbon double bond, and quite intense. So this means this is a polar. It may have a polar functional group inducing partial charge on the double bond. So you can check other stuff. If you have a formula, chemical formula given, and you find oxygen, then you have to say, oh, there is an oxygen. If it's not the case, there's nothing else but just carbon and hydrogen, then how do you create some dipole moment in the carbon single and double bonded alkene compound? So one proposal is like assuming this type of cis form of alkene. There you can have just carbon like this. You can have sp3 neighboring carbon donating electron to the more electronegative sp2 double bond carbon, and you have two of them as a cis isomer. Then you can add up those two vector, then you have the total dipole going down stronger, and that way you can see the carbon hydrogen and carbon-carbon double bond, they are polarized, especially double bond. So it could give you stronger absorption. So you know more than just alkene out of that spectrum. You know that the spectrum showing cis isomer, not trans isomer. So the answer for this is indeed this spectrum is the one from the cis pent 2-ene. Take a look at this spectrum and find out, what do you see? You see this big. It's around 3,300, but I told you don't pay attention to the number. Does it look like a OH or NH? Not really, right? You know, OH and NHs are normally broad. If you want to confirm, if you have OH on carbon chain, you're also supposed to have a CO single bond. So where is that CO single bond? You should check around 1000 here, but you don't have anything intense. So you can confirm and eliminate the hypothesis of OH being free. And normally OH free is not coming down this much. It goes more toward the this end. So it's not OH, it's not NH, so it must be CH. And what CH can be this much you know, frequency, not very close to the 3000. One of the most stronger bond of CH is from SPCH. And you can also say, why is it so intense? There's only one hydrogen. Maybe because that's a polar. So why the SPCH is polar, we'll see. But one hint I gave you was, if the triple bond is located at the terminal, not in the middle, it normally is a polar. So you check the presence of the triple bond to make sure this is indeed from the alkyne hydrogen. Then you go to the triple bond area, 2200-ish. It's right there. It's around 2100 something. And it's quite intense as also triple bond. That's again is telling us that the triple bond present in the not middle, but in the side. Then again, you see the casual sp3CHs and nothing special. And we don't want to say these are aldehyde because first, the number is not quite 27. Also, you don't have any carbonyl, so you skip. Those are the noises. And you go to the under 1500 level, so they can be anything from bending, and nothing is so significantly strong. So we have to be safe. Unless you have other data supporting the presence of something like a benzene or something, right? So we have to, for now, say we have alkyne with a triple bond at the terminal. So the actual answer for this is hex 1-ine. You have a 6 carbon and triple bond at the end. This example will shock you and make you search for multi evidence. This IR will tell you that you have little signal here over 3000, so you're looking for probably chance to be alkene or alkyne, and look around 20 something and you see tiny peak, but you want to ignore it normally. And then you go to 1500-ish, you don't see anything, but you have something around 16 something. So that's not carbonyl. So you might want to say this is alkene, and it could be alkene as well here. So you want to give best bet. This is alkene. Okay, this one's not easy to find out. Let's give it a try. You have alkane CH stretchings, and you see here little peaks that's strong enough to be aldehyde, and the locations are almost right, but again no carbonyl, so no aldehyde. And you see a little one and you want to ignore. and you have a bending vibration, so you cannot do anything more risky assignment. You don't want to match with anything. So you may say alkane, but the answer is actually this spectrum's from alkyne. And alkyne, you expect some CH stretching over 3000. Not really, right? If you have a triple bond in the middle of the molecule, you don't have CH, so you don't see that. And then around 21, 22-ish, you have something, but that's too small. That's why earlier I was hesitating to skip it all the time, so if the alkyne is a symmetrical, I said symmetrical, then the triple bond carbon bond could give you weak absorption, very weak absorption. This is the case. This you have to assign as alkyne. How do you know? This is not very convincing. That's why you need to use multi information for it. So if you have any other piece of information, you have to use it. Okay, I think I will come back to this, so please bear with me. But with the little other pieces of information, such as NMR or other UV and data, you can easily do it. But even with the information from the formula, you are able to find out this as an alkyne. So please, you cannot again simply look at the spectrum and assign the major peaks and then try to fit into the answer. That's not a good attitude. So I'll come back to this. Okay, let's look at the different functional group. If you have the isopropanol, this is what you expect. The OH is over 3000, broad and very tall, intense absorption. Then the CH around 3000, but they're all below 3000. So you can suppose that to be sp3 carbon hydrogen alkane peaks. And 27-ish, you have some spikes, but for now you can ignore. And nothing significant in triple bond area, and you are entering double bond area, but you pass the 1700, nothing. So there is no double bond here. CO double bond here and aldehyde at 27, that is, you can ignore that now permanently. And then you enter the 1500 below area, so a lot of bending vibrations. But then why those bending vibrations are all tall? That's because you have a polar functional group. So oxygen's polarizing this small molecule all over the place. So everything became so intense and capturing photon easily. And here you see one of the most intense and broad peak, that is a CO single bond, and that can come over 1000, and other bending vibrations. Here you can find butanoic acid with a carboxylic acid functional group, very broad, but as I said the other day, this could have been symmetrical, but you have some spikes. That's because if you look at the area that's below 3000, so you can assume that you have some alkane peaks, and it's hard to tell whether you have a alkene or alkyne. It looks very smooth, but there's a little thing there, so we have to keep that in mind, but that's not strong enough, so we ignore that for now. And then you go around 22 area, there's nothing almost. and this peak very intense and somewhat broad, so we assume that's a carbonyl group. You see the numbers, even 1700 and little more, and intensity and the feature of the shape tells us that this is a CO double bond. So remember this feature for the CO double bond. And then below 1500, you don't want to say much because you have carboxylic acid able to polarize most of the molecule, so the bending vibrations are quite intense. So any stretching signals that normally comes here is buried by those bending vibrations, so it's safe to avoid that. Okay, here I have one simple aromatic compound with the methyl group, the toluene, and what do you see? You have 3000 here and a bunch of the CH stretchings, but few of them appeared over 3000. So they are from either sp2 or sp carbon hydrogen stretching. Then you go 22, there's nothing, so this must be double bond. But why do you have so many? So you assume this could be aromatic. So, you know, pretending that you didn't know this was aromatic compound, this is how you get hint whether you have just alkene or aromatic. Also, you go to you know, a double bond area because you think this is alkene, not alkyne, and you have to confirm. You go here and you find the 1600 signal, right? Because of that, you think this could be alkene, but you have a couple others, and this is quite tall, so it may not be the regular bending vibration. As you can see, the general bending vibrations are small, so we assume this is from the real sample. So the presence of a multiple double bond, we can, you know, combine with this information, and we can say this is aromatic. So please learn how to get the hint about aromatic ring, not just alkene. So whenever you encounter evidence for alkene, you have to double check whether this is just alkene or aromatic. Okay, what do you have here? This one draws your attention. This is the highest number, but not close to 3000. So this is not CH. It must be OH or NH, but it's not broad like a normal OH. So this must be NH, but not really NH, but because you have a 2 vibrational mode. The NH, the secondary amine, will give you only 1 stretching. So this is a primary NH2 amine. So you have NH2. That means you gotta have a CN single bond. Most likely that's giving smaller force constant than carbon oxygen. So you are expecting them come around here. And it's hard to assign for now. But anyway, then you look at the CHs, anything below 3000, that's what you have. So there's no alkene-alkyne situation, obviously no alkyne triple bond. And to be alkene, this is too broad, and that as well is too broad. So this means you have some intermolecular force of the bending vibration that made the value little greater and then broader. So these bending vibration happen to be broad because amines are forming strong intermolecular interactions. So what we can say with the confidence is this compound is amine compound, primary amine compound. So answer for this is actually propylamine. So, you know, as we go through this, you're not just memorizing number, you are learning the features, the practical examples with a lot of variations, right? So again, here you see a little weird looking mountain kind of thing. I mean, not mountain, it's upside down mountain, so it's a little valley. Absorption. This is not quite OH, because OH should be somewhat intense. So this is a amine. Is it primary amine or secondary amine? And in my experience, to be a primary amine, you gotta have two exclusive peaks, and it doesn't look like it. So you might say this as a secondary amine with only one hydrogen, NH. Then no double triple bond hydrogen, no alkyne alkene hydrogen, that's what I meant. And also there's no alkyne triple bond at 2200 ish, and no carbonyl group, but you have some bending vibrations, but I don't want to bet on anything because that's just somewhat polar bending vibrations due to the nitrogen presence. So I just want to confirm, only based on this NMR at the sophomore level, this would be just a secondary amine with a bunch of alkyne chains. So this actually is two propyl groups on the secondary amine, so dipropyl amine. Okay, let's try this. You have none of the CHs or OH and NHs over 3000, and you have very isolated sp3 CHs by some reason. It probably means you don't have much of different types of alkanes. This must be a very simple molecule. And some of them you can read 2500, 26, 2700, and then 2800. You see those two. So we suspect aldehyde. And those three are probably from a couple alkane signals. And you have nothing until here, but that's about 1720 or something. So this is a good peak, because it's intense and a little have a little width, broadness. So ketone combined with the information about these two, and you can say this is aldehyde, and the molecule has shown some bending, which is weak. So overall the molecule is not that polar. So indeed this is the IR spectrum for propanal aldehyde. So this one also can be good practice, because someone may match this with a NH2, but intensity wise you don't want to say it, especially when everything else is so tall relatively. That's too small. Just keep that in mind though, there was such thing. And then over 3000 you see a couple signals, even there's a little shoulder here. So there is a chance to have some SP and SP2. But also again, these are a small number, and this number is not quite over 3000. That's right on the 3000. So we're not sure this is really the case with the SP or SP2. When you look at the 22, you do see strong, and that's actually too strong to be alkyne. So the other type of triple bond is a cyanide, right? CN triple bond. If we have a CN triple bond, that means we don't have SPCH. So this is not SPCH, and those are not as well. Then you go to double bond area, and you already enter the bending vibration area. So it's fairly difficult to believe them as SP carbon double bonds. So the best guess, only based on this IR spectrum, would be you have nitrile, CN triple bond. So this is a practical lesson. You have to ignore this intense signal and those NH2 looking signal, and this number is awfully close to be alkene or alkyne CH, and these are as well there, unless you have other evidence. If you do have other evidence, I will give few seconds to check on other signals, such as this presence of alkene in addition to the cyanide, and also these peaks. But otherwise, that's it. So yes, this is the practical experience that teaches you about the real example. Okay, what do you see here? What do you have? You have a signal over 3000, not NH, not OH, right? So it must be alkene or alkyne hydrogen. Then you check the presence of triple bond. That's easier one, around 22, nothing. And then you check something for carbon-carbon double bond presence, and you go to 1600, and you have some things, especially this one. So we give assignment here for CH stretching. Then all these bunch, those are alkane area of the molecule, and I don't see anything near 27 or 28. Then you go to signal here that's over 1700, so you give carbonyl group without knowing what it is exactly. Then out of this, we also said earlier, we have double bond. And when your idea come to this far, you have to check, like I mentioned earlier, whether this is aromatic or just alkene. Again, with the other spectrum, you want to double check. Only solely based on this IR, I want to say I see only one signal, and I only have one extinctive one close to 1600. Anything around the 1500, I'm gonna ignore almost. So I want to say this one is just alkene, and that's it. But I want to talk about variations now. Here, I have a similar spectrum. Okay, before you compare the two, you find similar thing: alkene, alkane, carbonyl, alkene here, and bending vibration in fingerprint region. And together, you also find the presence of carbonyl and alkene. But what is the difference? There are two things you need to find. One, the intensity for the CH is increased, right? Also, the intensity for CC double bonds, the alkene got more intense. What does that mean? So the change of the intensity is telling you that alkene became more polar. And if you pay attention to the number, you also can get some idea, especially the carbonyl group. The carbonyl was over 1700, but now it's below 1700. I don't want to give you exact number. This is the made up spectra. But my point is, if you have a certain number of carbon, you have some alkane, but you have alkene, and then you have carbonyl group. And you can think of an isomer sometimes when you run reaction, right? You have a carbonyl group, and you can have alkene. Then can you assign that which spectrum belongs to which compound. And again, you can look at the structure and find out. So when you look at this compound, you can see the resonance. Resonance will give this carbon positive. Since I'm not showing resonance structure, let me just give partial positive, like an average of the two resonance structure, and the carbonyl becomes also more polar. Here you cannot have a resonance, so you can say the more polar signal that came from this matching with this structure better, and weaker signal for alkene coming from this matches and explaining this structure better. When you do synthesis, you'll see this type of comparison. Then also that explains the CO double bond. It should be around 1715, but there is a resonance that is breaking the double bond. So the double bond becomes half and 1.5 bond. So the K value becomes weaker, smaller, so the frequency should drop. So it makes sense. Without resonance, it was a higher frequency, now it's a lower frequency. So that resonance also fit into this spectrum better. That's the one type of variation that can happen, and changing the intensity, the Y value, and the X value. All right, what do you have here? Some signal over 3000, no OH, no NH, no triple bond, so this must be alkene hydrogens. Then you see some of the alkene carbon double bonds over 1450, close to 1600, and it's safe to say you have alkene. However, you have again double check whether you have just alkene or aromatic ring. You have a multiple H's and multiple double bonds, though they are weak, right? Only because you see couple over 1600, you have strong case for aromatic. But if you have a better spectrum like an NMR, you want to confirm. Otherwise, this can be a risky assumption as well. But for now, you say I have alkene. I'm sorry, aromatic ring alkene. Then you have a small number of alkane, and then you have a carbonyl group. Okay, so I found the carbonyl, I found some alkane, I don't know how many carbons, that's all. And when you connect them, what you don't want to is shown next. You need to know the variations so you can connect these pieces together. There. This uses same exact pieces, but it happened to show different spectrum. Again, do not compare yet, but figure it out without comparing, because you don't always have a chance to compare. So look at them. The sp2 or sp3, you check 22, and that's not there, so it's a sp2ch. And you check sp2 area over 1450, you have a couple signals, but you still wonder, like, why is it so tall, almost as tall as a CO double bond? So something must be very polar. And then you notice, like, oh, this was a tall as well, so something is conjugated, or some electronegative group is next by. And then you notice the CO double bond, the 1700 area, a little less, or it could be, you know, on top of it, or it could be slightly bigger than 1700. You know, either case, you see that as a CO double bond, but it's weakened. So again, the theory of resonance present in the molecule explains this. Then you go back to what pieces I have here. I have aromatic, bunch of hydrogens. And then I found carbonyl group, and I found couple sp3 CH hydrogens. Then you say, oh, these are intense, polarized. So why the ring is polarized? What is there to polarize the ring? Here, the polar functional group with the resonance ability. So you combine these two together only because you have these intensified peaks and the wave number shifted to the lower, weaker K value area. So you connect them, you come up with this. Then you have some number of alkane. You don't know how many, so you assume you have it here, and that is your best guess. If they gave you a formula, then you can know how many carbons are there. I think we're gonna be working on that on next video. All right, so go back to the previous one. Now you know what you should be doing before you had this in your mind, right? Even when you solve this, you should be thinking about this situation to avoid the mistake of making up this one. So here you have these pieces, but you don't want to put them together because the rings are not polars and hydrogen on the rings not also polar. Also, the carbonyl is giving the typical carbonyl number. So it's not conjugated carbonyl, it's typical carbonyl. In order to be typical, the resonance must be avoided. So you do this. You put, I don't know how many, depends on the formula they give you, but then this is bound to the carbonyl group, so you can avoid the resonance. So this is how you apply the variations, keeping it in the mind, and then try to rationalize as much as you can for the given spectrum. So we can monitor all these reactions we could do from here to there. We can check the CBR peaks coming around 600 to 700 reciprocal centimeter, and you can check the double bond. This double bond around 1600 to 1450 or CH over 3000. And again, this will be similar to that. There's no way you can separate them with IR, so you need to based on the NMR. And these are the easy ones: strong, broad, intense peak. In the first box, from 4000 to 3000 for OHs, and you cannot tell them apart. And you can get the CO double bond, the typical ketone, so 1715 ish. And if you do ozonolysis completely, you get the maximum oxidation state. You get the ketone around 1750 and another carbonyl group that's around the 1715 as well, but you have a strong OH peaks and very broad, more than normal alcohol. This case you see two carbonyl group that's a regular, but you see the aldehyde signal as well as all the alkane peaks. So you can follow these synthesis, so you are getting ready to work in the real lab. But I want to touch upon carbonyl groups. And our lesson also, what we have left is learning more reactions on alcohols and ketone aldehyde and carboxylic acid, or the ester out of the alcohol or the carboxylic acid, amides, and those things. So let's give more attention on the carbonyl, and you can get more sophisticated little changes giving good information for structure. You can catch that with it. So theoretically, the regular carbonyl aldehyde and ketone, they have a slightly different number, but let's just say it's around 1715 reciprocal centimeter without anything. Attachment on the carbon and hydrogen will give certainly different reduced mass and also different force constant, but the difference is really small. So this is good enough for both of them. Then we talked about the resonance, right? Whether you have a regular alkene or the aromatic ring here, or even bigger rings, you have a chance to weaken this double bond K value. So you normally get around 1680 something, say 1690, because anyway the number is not precise. The point is this number gets about 25 to 30 reciprocal centimeter weaker. However, that also depends on what you have here as just substituents, or here or here or there. So the number can vary. Also, the resonance is not always happening with only double bond, right? You can have a nitrogen on it. Nitrogen is a fairly good electron donor. These are the atoms you find in the peptide bond of the amino acid of the protein. When you have that, the donation power of nitrogen is much greater than that of the double bond, because double bond is not as basic as nitrogen. So you can imagine this can be very low, 1650 something. Say let's say 1650. So a lot more weakened carbonyl group you get compared to this, and from the original carbonyl group it's way down, about 60 or more. Then you can say, how about oxygen? Let me put it here. Is it okay in the screen? Yeah. So if you have oxygen, it could be ester or carboxylic acid, but let's make it ester. Ester can also act as, oxygen of ester can act as electron donor and do that. However, if you give electron to, you are making oxygen negative using the oxygen. So you can assume this donation is not as much as this. Also, while the resonance is weakening the bond, you have strong electronegativity of oxygen, able to make the carbon more electronegative. Thus, the electron here becomes somewhat more stable inductively. So inductive effect and resonance effect working against each other, and the outcome is, it could be over 17, to be safe, 1735. It could be sometimes 1732 or something, but safely speaking, it could be this, which means resonance effect is not as much as the inductive effect of the oxygen. Oxygen is really electronegative, making this K for this bond greater. Another common atom you find around the carbonyl group is actually chlorine. Then you can use the resonance effect and inductive effect to deduce the number. Can you try, please, while I'm writing this down? Resonance in case of breaking bond, right? Resonance does not always breaking bonds. Resonance breaking double bond. Inductive strengthening carbonyl. Therefore, this makes the K smaller, this makes the K bigger. Okay, so resonance. Yeah, chlorine can do resonance. However, you know chlorine is not a good base. They don't donate electron, not even as good as oxygen. You know it from our earlier study. So resonance is not working much, so the bond weakening is not there. However, chlorine is quite electronegative compared to the carbon and the hydrogen, so there is some bond strengthening effect without any resonance, right? Unlike here, you have quite a bit of resonance, but you have more inductive. So what happened when you have this kind of situation? Surprisingly, it gets sometimes more or close to 1800. Surprise, surprise. I hope that you learned that how to use the resonance and inductive effect, so you can freely deduce the variations happening around the carbonyl. Not only carbonyl, any kind of situation. It's fun if you look into more detail though. So the carbonyl bonds are shifting. So when you see the location of the carbonyl around 1700, you know exactly what is going on the carbonyl, what are the neighbors and environment around. But also, when you pay attention to the oxygen single bond here, you have two kinds of single bond here for the ester. You have regular sp3 single bond with oxygen, and this single bond here is between sp3 oxygen, sp2 carbon. So we did this in the very early video, but this one does not have chance to do resonance. Therefore, this number is always static almost. They're near 1000. But this one here can change. Depends on what you have here. Anything here is promoting more resonance by withdrawing electron. Then you have a more strengthening effect and more weakening effect here. So this single bond becomes 1.5 bond. Therefore, this goes as high as 1300 and more even. I think I mentioned it in the beginning of the previous video. So if you see strong intense signal around 1000, that's supposed to be a single bond, then you can search for 1300-ish intense peak. That will give you idea of indeed you have ester. So in order to have ester, not, you have to compare not ketone with the ether. See, ether can have 10-1100, again the other 10-1100, two peaks, and you have 17 something, right? So you know this could be the case, not this sometimes. So only key to differentiate those two kind of isomers would be finding this intense CO single bond, or you pay attention to the number more carefully. But I would bet on this more than this number, and here is the why. Okay, so here, if you only pay attention to the different numbers for the different functional group, of the carbonyl, there is a problem right there. So cyclohexanone 1717, that's close to the typical carbonyl group. And if you go to cyclopentanone, the number jumps to the 1745. That's pretty close to the ester carbonyl group over 1735, casually 1740 something. And then if you reduce the ring size even more, it's a 1783. And even more, it becomes 1850 for the propanone, cyclopropanone. Then that's get confused with the value for chlorinated acid chloride functional group. So when you remember how to distinguish them, the different number for the carbonyl is the first step. But when you confirm, you do as much as with the more confirmation. In this case, for the ester, you have to look for this peak. And if you have other spectrum, NMR, mass, you want to check with them as well. This also is true for the ester. If you put ester functional group here, these numbers, it's not going to be 1717. If you have an ester here, it'll be more than 1735. And accordingly, having oxygen there, making more inductive effect on the carbonyl group like we did before, all the numbers will increase. But the point is, it's not just the functional group itself changing the number, but also the environment. Okay, I ended up videotaping too long again because it's difficult to cut in the middle. My apology there. But to wrap up, I want to have one more point made and one exercise. So we practiced on, when you get the spectrum, how to deduce the structure. Yes, I admit that that's the usual case as the researcher, but if you think about it, it's not always the case. If you run E2 reaction, you are wondering like if my base is big enough or not big enough to do Hoffman. If it's not big enough, you don't know, but if it's not big enough, you expect some Zaitsev product. So when you separated them with a column chromatography or something, you are holding the major product in one test tubes, and when you run it though, it's always the case the researcher will have the spectrum of the two isomer, both isomers spectrum in their mind. Then after running spectrum, as the printer print out the spectrum, you match right with the structure you have in your mind before the machine is printing out. And then you know what isomer you got. So you need to also be good at deducing spectrum based on the structure. So let's try one example, and hopefully I can make up more video later. Okay, this compound. So first step we do is you need to find out what functional groups we have. Then you know the typicals. Then you have to think about the variations. In drawing spectrum, it's the same for the reading spectrum, but you need to know the X value. It has the typical values and features about the shapes of each peak. But you have also variations for the X value. But also the typical Y value according to the polarity and the variations of the intensity you think about. So first you find here sp3 carbons, right? sp3 carbons holding hydrogen, and you find sp2 carbons holding hydrogen, as well as you find the CC double bond and the CO double bond. Then you can immediately think about the typicals, but is there any complication for variations? Here you can expect some variations because you have a conjugation, so please keep that in mind. Conjugation gives polarity change, also the frequency change. So when you start, think about the fingerprint region also, keep that in mind. First, you go for highest frequency of all is this one, right? So you put they're coupled, but you put somewhat intense, sharp sp2 carbon H stretching due to the resonance. Putting resonance sign will help you to remember the complication, I think. Then you have several hydrogens on the sp3, so you want to make it intense, 7 times intense, right? So something like that. And you skip 2200. I hope you noticed that I want to put these numbers first. Those are the essential ones. All the hydrogens, and then triple bond, double bond carbonyl, and carbon-carbon double bond, and then bending vibration. So you can see some of the CO single bond here, and halogens. So those are the essential numbers that you need to be aware. When you pass that, then you approach, you did this, so you approach area for carbonyl, and you had a complication there, so you pass the 17 and you show quite intense, not sharp, but somewhat broad carbonyl. Then you have carbon double bond, so one somewhat intense, right? Because it's getting polarized. Then you can start showing random bending vibration. So you bending, but you don't have a CO single bond, so it's okay. So this should be enough. And I hope you get ready for next video. I'll see you then.